Current electronic commerce is fundamentally constrained by the necessity of trusted third parties. This research details a robust mechanism for enabling payments over a communications channel entirely independent of central intermediaries. This historic paper, Bitcoin, a peer-to-peer electronic cash system, is authored by Satoshi Nakamoto. The foundational challenge of electronic commerce is its inherent reliance on financial institutions functioning as trusted third parties for payment processing. This trust-based model introduces significant transaction overhead and necessitates the mediation of unavoidable fraud. Consequently, a robust mechanism is required to enable payments over a communications channel without needing this central intermediary. We propose a purely peer-to-peer electronic cash system based on computational cryptographic proof instead of institutional trust. This presentation will detail the core architecture, focusing on the distributed proof-of-work mechanism used to establish chronological consensus and resolve the critical problem of double spending. We will examine the operational sequence for achieving network consensus and analyze the structural mechanisms for managing data and ensuring privacy. Finally, we will conclude by formally analyzing the mathematical probability of a successful attack against the proposed system. The foundational challenge of electronic commerce is its reliance on financial institutions functioning as trusted third parties for payment processing. While functional, this trust-based model harbors inherent weaknesses, primarily related to the necessity of dispute mediation. The cost associated with mediating disputes increases transaction overhead, effectively limiting the minimum practical transaction size. Furthermore, genuine non-reversible transactions become impossible, forcing merchants to accept a percentage of unavoidable fraud. A robust mechanism is therefore required to enable payments over a communications channel without needing the central trusted intermediary. The subsequent discussion will propose an electronic payment system based on computational cryptographic proof instead of reliance on third-party trust. Building on the prior discussion regarding the reliance on trusted third parties, this section introduces the fundamental goal of the proposed system. The objective is to implement a purely peer-to-peer electronic cash system. This system must allow payments to be sent directly, thus eliminating the need for central financial institutions to mediate transactions. While digital signatures provide necessary authentication, they are insufficient to prevent the critical problem of double spending without external oversight. Therefore, a novel peer-to-peer networking solution is proposed, utilizing hash-based proof-of-work to sequence and timestamp transactions. This mechanism forms an immutable record, which will be explored further in the upcoming discussion of the double spending problem. Following the proposal for peer-to-peer electronic cash, the fundamental challenge of double spending must be structurally resolved. An electronic coin is defined structurally as a chain of digital signatures linking previous transaction hashes and the next owner's public key. While this structure verifies the chain of ownership, the payee cannot verify that the coin has not been simultaneously spent elsewhere by a previous owner. Historically, this risk was mitigated by introducing a trusted central authority, or mint, which checked every transaction. This solution, however, reintroduces reliance on a trusted party, which the system is designed to avoid. To eliminate the mint, all transactions must be publicly announced, necessitating a method for participants to agree on the definitive chronological order of events. This agreement is crucial for establishing the earliest valid transaction. We previously identified the fundamental challenge of ensuring chronological order when operating without trusted intermediaries. The initial solution proposed to address this involved the use of a robust timestamp server. A timestamp server functions by generating a cryptographic hash of the current block of items to be recorded. This calculated hash is then publicly broadcast or published across various external media. Widespread publication provides mathematical proof that the data must have existed at the precise moment the hash was generated. Crucially, each subsequent timestamp incorporates the hash of the preceding timestamp in its calculation. This continuous linkage forms an irreversible chronological chain. reinforcing the integrity of all prior records. Building upon the concept of chained timestamp servers, a mechanism is required to implement this structure in a distributed peer-to-peer environment. This mechanism is the proof-of-work system, analogous to Adam Back's hash cache. Proof-of-work involves searching for a specific value, called a nonce, that when hashed with the block data, produces a hash starting with the required number of 0 bits. Once this substantial computational effort is expended, the block cannot be modified without redoing the work for that block and every subsequent block in the chain. Furthermore, the proof of work solves the problem of decentralized governance by establishing a one CPU, one vote system. The true network history is determined by the chain that possesses the greatest cumulative proof of work, known as the longest chain. Having established the proof of work mechanism, we now detail the operational sequence defining how the peer-to-peer network achieves global consensus. Initially, new transactions are broadcast across the system and gathered by nodes seeking to create the next block. These nodes then engage in a competitive process to find the requisite proof of work solution for the block they assembled. Upon successful discovery, the winning block is instantly broadcast to all participating nodes for immediate validation. Critically, nodes only accept the new block if all included transactions are legitimate and have not been previously spent. Consensus is maintained by continually extending the accepted block, following the rule that the network always considers the longest chain to be the single correct history. Maintaining the integrity of the peer-to-peer network requires mechanisms to reward contributing nodes. The primary incentive structure dictates that the first transaction in every block generates new currency, known as the block reward, awarded to the successful miner. This creation process facilitates the initial distribution of coins into circulation, mirroring the resource expenditure required in gold mining. Furthermore, incentives are also derived from transaction fees, which are the excess input value relative to the output value of a transaction. As the currency matures, the funding mechanism is designed to transition entirely to transaction fees, achieving an inflation-free state. Crucially, this reward structure encourages rational actors to remain honest, as they gain greater long-term profitability by following the protocol rather than attempting to defraud the system. To efficiently organize and verify the potentially large number of transactions contained within a block, a cryptographic structure known as the Merkle tree is employed. Individual transactions are repeatedly hashed in pairs until they converge into a single, unique value. This final hash, referred to as the Merkle root, is the only transaction-related data included in the block header. This design allows any network participant to quickly verify that a transaction was included in the block simply by checking its hash path against the root. Crucially, once a transaction is deemed sufficiently buried under subsequent blocks, the spent transaction data can be safely discarded. The Merkle tree facilitates this disk space reclamation by allowing the pruning of entire branches, keeping only the remaining hashes necessary to maintain the integrity of the root. This capability is essential for managing the long-term storage requirements of the system. Following the explanation of the Merkle tree structure, the system can efficiently manage its persistent storage requirements. Once a transaction is deeply buried under a sufficient number of subsequent blocks, the spent transactions associated with it can be safely discarded. This process is made possible because the Merkle tree secures the block's hash using only the root of the transaction tree. Consequently, old blocks can be compacted by stubbing off the interior branches of the tree, eliminating the need to store the detailed transaction hashes. This ensures that only the compact block headers must be perpetually maintained. The system estimates this leads to a minimal yearly increase in storage consumption, estimated at 4.2 megabytes annually. Building upon the concepts of the Merkle tree structure, simplified payment verification describes how a user can verify a transaction without requiring a full network node. A lightweight client does not need to store the entire ledger. It only needs to keep a copy of the block headers from the longest proof of work chain. Verification is achieved by obtaining the specific Merkle branch linking the transaction back to the accepted block header. Linking the transaction to a timestamped block confirms a network node has accepted it, and subsequent blocks further solidify this acceptance. This simplified method, however, inherently relies on the assumption that honest computing power controls the majority of the network. While efficient simplified verification is more vulnerable to fabricated transactions if an attacker can overpower the network. Therefore, businesses handling frequent payments are generally advised to run full nodes for superior independent security. Following the establishment of the network infrastructure, it is necessary to examine how value is transferred within the system. While tracking every individual unit of currency would be theoretically possible, efficiency dictates that transactions must allow for the combining and splitting of value. To achieve this, transactions are constructed to accept multiple inputs, aggregating smaller amounts inherited from previous transactions. Conversely, the mechanism supports multiple outputs, enabling the distribution of the consolidated value. These outputs usually consist of the payment amount directed toward the recipient, and a second output returning any necessary change back to the original sender. This structure ensures that value management is both flexible and scalable within the peer-to-peer electronic cash system. Previous slides detailed how transactions are structured and verified. The current discussion addresses how privacy is maintained when all transactions are publicly announced. While the traditional banking model relies on limiting information access, the necessary public visibility of the distributed ledger requires an alternative approach to privacy. Privacy is instead achieved by maintaining the anonymity of the public keys used in every transaction. The public ledger reveals that an amount has been sent from one address to another, similar to a stock exchange, making the size and time of trades public without revealing the parties involved. Furthermore, generating a new key pair for every transaction acts as a vital firewall, preventing transactions from being linked to a common identity over time. It must be noted, however, that multi-input transactions inherently introduce linkage, revealing that the specific inputs share a common owner. Having established how transactions are recorded and verified, we must now formally analyze the probability of a successful attack. The attacker's capabilities are fundamentally restricted. They can only attempt to reverse one of their own recent transactions, not generate new wealth or spend others' funds. The competitive extension of the chain, by honest nodes versus the attacker, is mathematically characterized as a binomial random walk. Furthermore, the probability of an attacker overcoming a current block deficit is directly analogous to the classic gambler's ruin problem. Specifically, if the probability of the honest network finding the next block exceeds that of the attacker, the chance of the attacker catching up diminishes exponentially. This confirms that if an early lucky lunge does not occur, the attacker's probability becomes vanishingly small as the honest lead increases. Consequently, this model enables calculation of the necessary confirmation time for a transaction recipient to be certain the payment is finalized. The concluding slide addresses the overall system robustness, summarizing the architecture proposed throughout this presentation. The framework successfully outlines a mechanism for peer-to-peer electronic transactions that operates without reliance upon institutional trust. This objective is achieved by combining cryptographic digital signatures with a computationally intensive proof-of-work mechanism designed specifically to prevent double spending. The network achieves substantial robustness primarily through its unstructured simplicity, allowing nodes to operate simultaneously with minimal coordination or need for identification. This mechanism rapidly establishes a public history of transactions, making alteration by an attacker computationally impractical, provided honest nodes control the majority of computing power. Ultimately, all necessary rules and incentives are enforced through consensus, where nodes express acceptance of valid blocks by working to extend the chain using their respective central processing unit power.